We learned about k-nearest neighbor for classification, and then we moved into multinomial logistic regression. What happens in a multinomial logistic regression is that it's very similar to regression. So you have parameters 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters. You have your features x1, x2, x3, x4. These are your variables. This is where your input data is going to go in. But the problem with the output data is that unlike regression, where your output data was a continuous variable, now your output is a category. It's either a 1, a 2, a 3, a 4, a 5, etc. So it's a category. So we have to adjust the output of our model to give us the probability of the first category being the correct category, okay? The probability of the second category or the third category. And for this topic, I'm using the iris data. For the iris data, you had 4 variables: petal length, petal width, sepal length, sepal width. So this is x1, x2, x3, x4. And then the output was setosa or versicolor or another class. So you have 3 types of classes. And then you want to answer this question: what is the probability of the first class being true, the probability of the second class being the true probability, being the true class, or the third class being the true class? And then the way that you turn these two numbers, these are real numbers from negative infinity to positive infinity, z1, z2, to turn them into probabilities, you just take the exponential of z1, z2. This is going to make them positive because the probability has to be positive. Then it has to be less than or equal to 1. To make it less than or equal to 1, you divide it by a number that is bigger than the numerator. So your denominator is going to be bigger than your numerator. So P1 is less than 1. Similarly, P2 is less than 1. P3 is less than 1. So these are probabilities. At the same time, they have to add up to 1. So now let's check that. If you add 1 plus exponential of z1, exponential of z2, that's going to give you your numerator. And the denominator is exactly the same thing. And therefore, they're going to add up to 1. Now, how do you train? How do you find the best parameters? You do optimization, okay? Now, it is the time to look at your data. This is your model up until this point. Now you take a look at your data. You take your input data, let's say the nth row in your data, the first row, the second row, the nth row. If you take that, put it through your model, then you're gonna get 2 numbers, z1, z2, and then out of these exponentials, you're gonna get 3 probabilities. But then we want to increase the probability of the correct label. Okay, let's say your first row is x1, 1, x2, 1, x3, 1, x4, 1, and then y1. And because it is your training data, you know that for this row, y1 was, I don't know, versicolor, and versicolor is the second class. So you want to increase the probability of the second class. Equivalently, you can increase the probability of the log, actually log of the probability of the second class. Or equivalently, in machine learning, we like to minimize, so you multiply by a negative sign. Or equivalently, minimize the negative of the log of the probability of the second class. So whatever you do, you are increasing the probability of the second class. What does it mean? Because these probabilities have to add up to 1, if you increase the probability of the second class, you have to decrease the probability of the wrong classes because they have to add up to 1. And this is exactly what multinomial logistic regression is going to do. Any questions so far? And the question now is, where is this implemented? It is implemented in neural net. It's NM package. So you have to install the package and then load it. Then you create your multinomial. And then we are doing a multinomial logistic regression of species on the other variables, on all of the rest of the variables. Iris is our data. The algorithm is going to do some iterations and then it's going to converge. You can take a look at the summary of the model. These are your parameters. You have 10 parameters, you learn them, then you can use them to predict the probabilities. So this probability is dominating, so that's going to be your class, setosa. If you want to get the prediction for all of your test data, you just say model predict, and then these are the predictions of the model. Now you want to check how accurate your model is. You can look at the confusion matrix and see that the algorithm is confusing Virginica for versicolor, and it's confusing versicolor for Virginica. It's making 3 errors there, 2 errors here, and then in the end, you can report the accuracy, which is just the summation of the diagonal terms divided by all of the terms, the summation of all of the terms in your confusion matrix. You can do the same thing for the diamonds data. That one is more complex, but it's still, that's why it's taking more time. Then you do exactly the same thing. For the diamonds data, you have 5 classes, so your confusion matrix is going to be bigger. And then because it's a tougher data set, your algorithm is making more errors. In the end, the accuracy is 65.44. So this was a quick recap of what we did last session.